In this video, I want to show why the adjoint method for finding the multiplicative inverse of a square matrix actually works. Now I'm going to do this for a 3 by 3 invertible matrix. In this case, I'm going to call it A, and I'm using the usual double subscript notation that you see here for the various entries of cap A. I'm going to assume that cap X is actually equal to A inverse. So I'm also there using the double subscript notation. AX should be I, where I is the 3 by 3 multiplicative identity. That is the matrix that has ones down the main diagonal and zeros everywhere else. I'm going to use a double subscript notation there as well sometimes. Here, cap I subscript ij would be the element of cap I that's in the ith row and jth column of I. If I do that, you will notice here that cap I subscript ij is 0 if I and j are different, but 1 if I and j are equal. That's simply saying, once again, that there's ones down the main diagonal, zeros everywhere else. Now, I'm going to start here. I'm going to think about going A times X. From the way I have X and A written here, I'm going to start by multiplying the first column of X on A. And if I do that, I should get the first column of I for my answer. And I could actually break that down into 3 separate linear equations as shown here. This is simply showing the first column of A times X is equal to the first column of I. All right, so that should be clear enough here. Now let's think about how we can solve a system of equations like this using Cramer's rule. Now if you remember how that went, let's maybe start by trying to solve for x subscript 1, 1, or x sub 1, 1. So from Cramer's rule, what we would do is what? Take this matrix A, that is the coefficient matrix, and we would replace it by 1, 0, 0 in that first column there, 1, 0, 0. And then we would find that determinant of the resulting matrix and then divide by the determinant of A, written this way. It kind of looks like absolute value of A, but it's not. Okay? So this is what Cramer's rule would yield. Now, we're interested in writing this a little bit more simply. You know, if you think about this, with the 1 here in the position 1, 1, and zeros everywhere else in that column, when you compute that determinant, you're actually getting what we called the cofactor with subscript 1, 1 of A, and then we're dividing that by the determinant of cap A. So that's x sub 1, 1. This is what Cramer's rule would yield. Okay? Now, if we're interested in finding x subscript 2, 1, what we would do is take the coefficient matrix and replace it by 1, 0, 0. And that's what I'm going to do here, and take that determinant of the resulting matrix and divide it by the determinant of A. Now again, because we have 1, 0, 0 here, and we're going to expand around that middle column, what we're actually going to get is, from our definition, the cofactor 1, 2, because it's in the first row and second column of A divided by the determinant of A, and notice that's x subscript 2, 1, right? Okay, notice the relationship between the subscripts here and the subscripts here. Notice how they're written backwards, aren't they? Okay, and then if I do the same thing here finally with x subscript 3, 1, I would replace the third column of A by 1, 0, 0, leaving the rest of that matrix inside the determinant alone, and you could see when I take the determinant there and divide it by the determinant of A to get x subscript 3, 1, because that 1 is in what? The first row and third column, really what I'm getting is the cofactor 1 comma 3, or sub 1 3 of A divided by the determinant of A. And notice once again we get this reverse effect on the subscripts here. Okay? We can write 3 equations to solve for the second column of x and 3 equations to solve for column 3 of x, that is the inverse of A. In each case we find the following, that so you can just continue this yourself, but we would find x subscript ij is the cofactor subscript ji of A divided by the determinant of A. And if you think about this, this would be the same as the cofactor I subscript ij, just like this one, if we use, instead of A, we use the transpose of A. Okay? All right? But if you think about that, there's another way of doing this, forming x then this way. So I'm saying here cap x, which is really A inverse, is this matrix with, this is the component that's in the ith row and jth column here, is actually the COF sub ij of A transpose, that whole matrix, you see I'm using these, divided by the scalar, which is the determinant of A. Okay, so the cofactor sub ij of A transpose as a matrix divided by the scalar. That scalar would simply divide on each of the individual entries, and that's what we're saying here. So this is a little bit better way. But if you think about this as a matrix here, this is exactly the same as going the cofactor sub ij of A as a matrix and then transposing afterwards and dividing by the determinant of A to actually get A inverse. So this is A inverse. And this is exactly why this technique using adjoints actually works. Well, I hope you understood that. There it is.